Hello, everyone. Just want to make sure that you all can hear me. Could you please write in the chat box if you can hear me? Yes, okay. Mr. Rohit said yes. Okay, okay. So you all saying yes. I think now everything is okay. Give me a second. Could you please remove this sharing so that I can share my presentation?
Okay, Mr. Engineer Abdul Fattah, I will start by a 5 minutes presentation, then you can share your screen, inshallah.
Yeah, okay.
Okay, thank you. So welcome everybody to our webinar, Low Resistive Bay Petrophysical Analysis. I will start by only 5 minutes presentation about Reservoir Solutions Company. Reservoir Solutions Company is a training and consultation services center. Reservoir Solutions is a company specialized in providing technical studies and courses for oil and gas companies and professionals. The company incorporates many professionals with diverse technical background related to oil and gas exploration and production. We have many of services that we can provide. We can provide technical reservoir studies for oil and gas companies, field development planning, reservoir static and dynamic modeling, economic feasibility studies, technical support for academic researchers for gaining PhD and MSc degrees. So if you are a PhD and the MSc students, we can support you by the technical support by our professionals. Also, we can assist in writing technical papers and assist also to publish it. We are preparing technical petroleum courses like our upcoming course of PVT and equation of state modeling using PVT sim software. Also, we are providing mentorship programs. So if you need a help for a specific technical topic, we can prepare a program for mentorship by one of our professionals to help you. Our recent work for the recent technical studies, we conducted reservoir static and dynamic modeling for oil company located into Libya, gas condensate field development plan for a Turkish field, economic feasibility study for gas recycling project in Turkey, economic feasibility study for an offshore field in South of America. Recently, we conducted an interpretation for a well test for a client into the USA. Our recent courses, we conducted practical reservoir static and dynamic modeling, coring and routine core analysis, PVT fundamentals and the equation of state tuning, reservoir dynamic modeling using software, spatial core analysis and reservoir engineering applications, and integrated reservoir management. For the next courses that will be performed into the next period, we will conduct into the 5th of November, the next month, we will conduct a course of PVT and equation of state modeling using PVT sim software. Also, in the month of December, we will conduct the other course of practical reservoir dynamic and static modeling using Petrel software. For well engineering courses, we will provide well integrity management system course, fishing operations workshop, and production logging design and interpretation course. For the next course that we will have, we have the course of PVT and equation of state modeling course using PVT 7 software. We have many topics to be covered into this course, like reservoir fluid properties, experiments, sampling for reservoir fluid, PVT data adjusting and correction, PVT QC, how to deal with contaminated samples, reservoir fluid characterization using the black oil and compositional modeling, flow assurance studies, and EOR PVT experience. The benefits that you all have after enrolling of our course, you will have the recorded videos for the course, the study materials, the datasets, Excel application sheets, and at the end of the course, you will have 2 days for a project to apply all the theories and the practical, to have application at the end of the course. Also, you will have a mentorship after the course through the WhatsApp group of the course. For the course fees, for professional, it's only about 40 USD, and for students, only 25 USD. The course is certified and the certificate will be signed by the instructor. The course is about 7 days, and every day will have about 2 to 2.5 hours, and the last 2 days will be about 1.5 hours. Okay, that is the content of the course. Okay, so if you are interested in our course, you can enroll into it by the link that will be sent into the Zoom chat now. For our webinar today, please ask your question into the Zoom chat, and the moderator will collect all the questions to ask the instructor at the last minutes of the session. Mute your mic and camera. Fill in the form sent into the chat to get a webinar certificate. So if you wanted to get a certificate, please remember to fill the form or certification that will be sent into the Zoom chat within the session time. Join our Telegram channel for upcoming webinars and courses. If you have any question, you can contact us by the mail and the WhatsApp that will be sent into the Zoom chat. Thank you all, and Engineer Abdel Fattah can share your screen, please. Okay, I will unmute you, Mr. Abdel Fattah. Open your mic now.
Okay, can you hear me now?
Okay, okay.
Yes, okay. Can you see my screen?
Yes, sir, you can start.
Yes. Okay. Good morning or good evening, good afternoon, wherever you are right now. My name is Abdel Fattah Rashid. I'm a Petrophysics TA, an academic teacher of Petrophysics at university. Today we will have a webinar on a very interesting well logging or a petrophysical topic. It's a low resistivity pay analysis. We will go through, let's say, a bit of an agenda. Let's see it. Give me a second. Yes, here it is. Okay, our agenda today is what are resistivity, anisotropy, and bed lamination. We will first talk about those geological effects that would affect your well logs response, especially the resistivity response. That's the main concept that we are talking about in this webinar today. It's all related to the resistivity response and how you would in-simulate this response regarding the case that you're going through. In our case here, it would be a low resistivity pay, so we would go through this. Also, why would we have the resistivity anisotropy or the laminated beds, let's say sandstone laminated beds, cause a low resistivity in a certain depth interval. However, we have this zone to be considered as a production zone or as a base zone. If I have a base zone, which of course I'm producing hydrocarbon, I think as all we know, hydrocarbon considered to be having a high response of resistivity. So if I'm having a certain depth interval at a certain well, and I perforated this depth interval, and it produced hydrocarbon for me. However, the log response of the same depth interval on the well logs, it gave me a very low, relatively very low resistivity value. So actually how that would happen, that we will see today. Then we will jump into examples. We will have actually several examples here. We will go through triaxial resistivity examples based upon an RT scanner tool. We will go for the NMR example for low resistivity pay. We will talk about, I think not everyone would know about it, dielectric scanner. It's not kind of a fabulous or sorry, a common or a famous tool. We will also talk about it today, and also we will see how the borehole microimager or how the borehole geology imaging would be uh, beneficial or would be essential for you to evaluate your petrophysical evaluation for a low resistivity bay. So let's go for it. Okay, I think all of us saw this slide before. The normal and the basic get well logs for whatever the formation or the fluid that you have occupying a certain depth interval wherever you are around the world. I think we can all, at least for basics, we can say that the slide in front of you right now, uh, let's say, resembles the well logs response for, let's say, about 90 or let's say 85 or 80% of the cases that we go through regarding petrophysics. So when you go through the well logs, the main thing that you must have before going through any petrophysical evaluation is considered to be the triple combo. Triple combo is considered to be the resistivity log, neutron, and density, or the bulk density logs. And the gamma ray is considered to be a basic log for any wireline tool that goes into the formation. So triple combo goes for the resistivity, neutron, and density logs. So I think I don't want to waste so much time on this slide, so I'll just go through it because I think all of you know about it. For the gamma ray, it's considered to be a lithology passive tool. When you have a low gamma ray, I have a clean formation, not necessarily sandstone. You can sometimes have radioactive sandstone that would have a high gamma ray response. However, it's not shale or something like this. So sandstone is not always like this, but as I told you, this slide is considered to be giving you the basics of the triple combo well logging. then the resistivity log. Of course, the second track we have a depth. I don't think that we have anything to analyze in this. At the third track we have a resistivity. When you have a hydrocarbon, the resistivity considered to be high, and when you have a brine or formation water with a high concentration of salinity, the resistivity will be low too. So that's the normal thing that we know about it. Also, if we go here, let's say for the resistivity, gas is considered to be having a higher resistivity than the oil down here. Okay, so that's a very normal thing because gas is considered to be more resistive than oil. After all, oil is considered to be a liquid. Gas is considered to be it's a gaseous state. So gas is way more resistive than this, and actually it would reach to this area here right now. It would be so high. The upper limit here of the resistivity is considered to be 20 ohm meter. It's not that high. I think I'm sure that you saw resistivity pay, sorry, production pay or production diff interval that would have a resistivity value of way more higher than 200 or sorry 20 ohm meter. It was sometimes reached to hundreds, sometimes it was reached to 2000s. So this is not a example of a certain case. This is only a slide that I can just show you the normal response of the well logs of the very basic logs, which is triple combo. Also, then we can go for the neutron porosity and the bulk density. When you go for the API limits here, negative 15% to 45% in the neutron porosity, increasing from right to left, and the bulk density 1.9 to 2.9. Sometimes they put it 1.95 to 2.95, but it depends on the amount of on the information or the country that you are at right now. Sometimes I saw the neutron porosity from 0 to 60, and neutron porosity is from negative 0.5 to 0.55. So it depends on wherever you are and how the formation that you have deep down the ground actually resembles or responds to the wireline log. But as you see here, we have a gas balloon here, a very large crossover, the density on the left and the neutron porosity on the right. That's considered to be an indication for gas presence. Oil saturation have a higher resistivity, but also it's have a little bit shallower uh, crossover between the density and the neutron porosity. Also, the brine goes for the same thing, but it keeps going shallow, and that you can only get these crossovers when you have sandstone formation. You cannot have crossovers when you go for shale or carbonate or something like this. So you can get sandstone, you can get crossovers between the neutron density log when only you go for the sandstone formation. That's it for this slides. I just wanted to illustrate to you the main principles of the very basic well logging data set, which is a triple combo. So this is considered to be a low resistivity pay nugget. And by nugget, I mean I just give you a glimpse about uh, in this slide, and then we will go and see whatever we are going through here. So let's just look at this here in the far left track. We have the neutron porosity, bulk density, PEF, and the correction of the density. The second track we have array. Third track we have depth. Fourth track here we have some kind of the formation tops that you have for the each zone that you are going through. And here is the most important log in this slide that we are going through to talk about it right now, along with the far right log here. So resistivity, as you see here, is considered to be a resistivity log, and it's considered to be very low, as you see. I don't think that at this depth interval here, we have a very high value of resistivity, especially if you go for the deep resistivity. So if this begins from 0.2 until 200, in that area, I'm having a resistivity that would be equal to uh, 4 or 5 or at maximum 6 ohm meters in this depth interval. Okay. However, when you go for the same depth interval here for the volumetric log or the saturation logs, you see this green shadings here is considered to be hydrocarbon. Okay, and it's not low percentage or value of the hydrocarbon, it's a quite economic amount of hydrocarbon. So how would I have this amount of hydrocarbon considered to be at the same depth interval to or with a very low resistivity values as you see in front of you here right now? However, when we have a little bit higher resistivity values here, you can see that at the same depth interval, I don't have a hydrocarbon at all. So here, it's not at all related to the resistivity values here. Here, you cannot go for the deep resistivity value to consider it as RT and calculate the RW from the lab or from SP log or something like this. And you can just go and apply Archie's equation or whatever water saturation equation that you want to apply, and then get just water saturation values and subtract it from one so you can get the hydrocarbon potential. It doesn't go like this, because if you are going through well logging or petrophysics before, you would know that the resistivity values in this to the interval here, it does not resemble the hydrocarbon potential that we have in this depth interval or in this depth interval. So here it's not at all related to the resistivity here have something here is wrong. Whatever it is, the resistivity value is considered to be wrong, or the calculation of the hydrocarbon volume here, it's not considered to be very right, because this is what spiritual physics is about. You need to go for an interpretation for the whole data set of logs that you have in front of you at the same depth interval, and all of them need to let's say go along, so that you can say that I'm having actually a very good petrophysical evaluation that I did with a high percentage of accuracy or precision. But here, water saturation or oil saturation is, let's say, depending on the resistivity values. If you are going through Ausch's equation or Simandou, dual water, Indonesia, Watson Smiths, whatever the uh, equation that we will use to calculate the hydrocarbon. So I think that now here you can see that the hydrocarbon potential does not resemble the resistivity values. So now, why is this happening? First of all, I need to tell you something, that the resistivity value has nothing wrong with it. It's 100% right, and there is no any error or a fatal or sorry, a vital mistake regarding the data acquisition here of the resistivity data. Also, at the same time, you don't have any problem with calculating this hydrocarbon potential that you have here. It's not wrong at all, either of them. So actually, why does this, or why is this happening? This is the next slide that we need to go for. The resistivity values need some corrections before you can take it and go for your petrophysical interpretation. So if you are considered to be a client and you hired a certain service company, let's say an X company, to uh, acquire well logging data set for you, before they give it to you, the CD or the the hardware that you have the data on it, they need to go for environmental corrections first. Okay, these are considered to be the data or the geological effects that we need to for the that we need to do environmental corrections for it before we begin studying the data that we acquired. The only one that we are interested here right now is considered to be the anisotropy. Okay, by anisotropy, I need you to look at this here, or at this large uh, figure of it. Anisotropy means that either of two things. You have a certain zone, let's say it's a sandstone, okay, and this sandstone is considered to be having thin beds of shale within the sandstone layer itself. Okay, when I say shale, I think that you all know that the chemical composition of the shale content is considered to be having 8 molecules of H2O. So I have a lot of water there in the shale. So if I have a hydrocarbon potential in this sandstone zone, and this sandstone is considered to be sandwiched in between multiple layers of shale, it would reduce the value of the resistivity that I have. Hence, it would be misleading for me to know if I have a hydrocarbon potential at this depth interval or not. Okay, so this is a thing. When you have laminated formations, this is a thing that you actually can have a low resistivity bay at. So the first thing regarding a geological structure that you have that would cause low resistivity values, although you have a hydrocarbon, the first reason that we have is anisotropy. Anisotropy is considered to be one of two things: either laminated sandstone that I just told you right now. I have a sandstone layer having thin beds of shale inside it, and we see multiple examples regarding this right now. I'm just trying to give you the geological meaning for it, why the lower resistivity bay happens. So this is a thing, the laminated sandstone with shaly thin beds. The second thing of anisotropy, which considered to be the main definition of anisotropy, anisotropy means that at a certain depth interval, the rock properties, let's say as an example, the porosity, okay? The rock property that you have in a certain depth interval, it changes with direction. So if I have a value of a porosity at the, just give me a second, at the shallow depth of investigation of this LWD figure that we have in front of us, if I have a porosity here that would give me a porosity value of, let's say, 0.2, it's 20%. Okay, it's a 20%. If I am going horizontally deeper, it would change. Whatever it is, it would increase or decrease. But what I'm saying right now, so I mean that we are going through a heterogeneous reservoir regarding the direction that you are going through. If you are going in the x direction, the porosity value changes. Y direction, porosity changes. X direction, porosity, sorry, Z direction, porosity changes. So that's the problem. So if I have a value of a porosity in the flushed zone depth of investigation, we're talking about from 10 to 30 centimeters deep horizontally into the formation, okay? That would consider to be changing or having a porosity value rather than the deep or the medium depth of investigation. If I'm talking about resistivity value, let's take the set of resistivity values that Halliburton company goes by, let's say. So shallow, medium, and deep. So shallow is considered to be having a depth of investigation of 10 centimeters. That's about 4 inches. Okay. The second goes for, or the medium resistivity values goes for, let's say 50 or 60, something like this, centimeters deep into the formation horizontally. Please know that now I'm talking about the depth of investigation. So it's deep inside into the formation, but horizontally, in a horizontal direction, considering that the well that I have drilled in this formation right now is considered to be vertical well. Okay, and the deep depth of investigation of the resistivity tool, let's say it reaches to 200 centimeters, that's about 2 meters. Okay, if I take a point of the resistivity or a porosity at each point of those, I will find it to be changing. So the porosity is not constant along the path that I'm investigating right now. So this is considered to be an anisotropy, okay, or an anisotropic effect. So again, anisotropy is considered to be the change of the rock property with direction. The long you go deep into the formation, whatever the direction is, X direction, Y direction, or Z direction, the rock property that you are going through is considered to be changing. That's another thing for the anisotropy effect. So why could the porosity affect the resistivity value. Because if I'm having a hydrocarbon potential occupying, let's say, a zero point 0.2 uh, average porosity value in a certain depth interval, and this fluid is considered to be water, okay? So I would have a low value of resistivity, okay? But this is okay because this is, I'm telling you that this is water, so it's considered to be nothing wrong with it. There's not a low resistivity pay. After all, I'm producing hydrocarbon, not water. So this is okay. But if I have at the certain depth interval the same one that I had 2.0.2 or 20% of porosities here, considered to be occupying or in the flushed zone. So a little bit deeper in the deep investigation, let's say 2 meters or 200 centimeters, I would have a porosity of 5% or 4%. What would happen with the resistivity here? It would be a lot higher. Okay, but here this is considered to be misleading because if I'm having a 4% or 5% of positive associated depth interval, I don't know about you guys, but in my area 4 or 5% of porosity is considered to be not economic at all, even if it's have hydrocarbon inside it. So that's another example for the anisotropy thing. I just wanted to illustrate to you the physics, the geological structure that would cause the anisotropy strata or the anisotropic effect. So, what do you do to overcome this dilemma, the resistivity anisotropy thing? Normal resistivity logs that we know about is considered to be lateral log or induction log or microspherical. Okay, so we know that lateral log can acquire the resistivity values in a conductive porehole environment, which is water-based mud. Induction log can acquire resistivity values when you have resistive porehole environment, which is oil-based mud, and also microspherical can go for the water-based mud. What else can we have? Or actually, can those values of resistivities can go for us or can give us a go or can give us an opportunity to analyze the petrophysical evaluations that we need to go through regarding to a certain depth interval. I think from the example that I showed to you 2 slides ago, it's not. I was having a very considerable amount of economic hydrocarbon. However, the resistivity values was so low. So the resistivity values that you saw back then, it was considered to be a normal resistivity log. It was lateral log or induction log. So it wasn't reliable for us to use to build small resistivity logs. But you can do. So service companies came up with a new magical tool, to be honest. It's called triaxial resistivity tool. And by the word triaxial, as you see, tri means three. So not to go for the physics principle of the tool so much. It would take so much time, to be honest. And I have a lot of examples that I need to show to you. But let's go for the main thing about it. And I will recommend a book and paper that you can, a manual actually, that you can read to understand everything that you need to know about the physics principle of the tool here. But the triaxial resistivity tool, it gives you an acquisition of the resistivity response, 3 directions, X, Y, and Z. By the acquisition of the resistivity values in those 3 directions using some kind of a transmitter, which is called collocated transmitters. You can use this tool now or these 3 acquired resistivity directions measurement, X, Y, and Z, to obtain 2 things, RH and RV, as you see here right now. So RH is considered to be the resistivity value in the horizontal way. It's, in other words, It's the normal resistivity value that you get from any normal resistivity tool, whatever it is, lateral log or uh, induction log. Okay, so horizontal resistivity, there is no magic about it. It's normal. There is nothing new about it. We all know what's normal resistivity. So the horizontal resistivity is considered to be the same. There's nothing wrong here. Okay. What's new here is considered to be the vertical resistivity that you have here right now, and we will talk about it. Vertical resistivity is considered to be the most important thing regarding the low resistivity bay. If you are talking about solving anisotropic effect dilemma or low resistivity bay dilemma using a resistivity tool, because there are way more other tools that you can use to actually go through the anisotropic effect, and don't let it mislead you. But we are now talking about the resistivity log, so let's just keep talking about the vertical resistivity here. So as you see, horizontal resistivity, it gives you a reading of a resistivity response in a certain zone, as you see here right now. However, we have here considered to be shale bed. This is considered to be an isotropic effect, okay? So I have shale, sandstone with some coated sand shale grains inside of it, then shale again, then sand, then shale again. So if I'm using only the horizontal resistivity to, or the normal log resistivity to obtain these values here of resistivity, that will be very misleading, because this is considered to be a thin bed. So I'm having here thin beds of the shale that would have a high amount of irreducible water saturation that would affect my resistivity values. That's why when you have an anisotropic effect or thinly bedded shaly sand zone like here right now, you will have a misleading value of resistivity, which would be so much lower than it should be. So that's a problem with the horizontal resistivity value. However, when you go for the vertical resistivity, it's as its meaning. It measures the resistivity value not horizontally, like we all know about the normal resistivity logs, but vertically. So it would go through the whole depth interval of the sand that I have, and the whole depth interval, or in other way of depth interval, let's say thickness, okay? So it can go for the whole thickness of the sand, whole thickness of the shale, whole thickness of the sand, shale, and then sand again. So by doing this, you're having more accurate, or let's say more precise resolution of the tool that you are using right now. This is considered to be called a vertical resolution. I don't know if you know about, I know that all of us actually know about the depth of investigation of tools. It's a very common thing to know, all of us. But to go for the low resistivity pay or thin bed analysis or something like this, you really need to know what is the difference between the sampling rate and the vertical resolution. Vertical resolution is considered to be the thinnest bed of formation that a wireline tool or an LEWD tool can actually give you a reading in it. Okay, because the main problem about the low resistivity bay, that they are here thin beds. Just give me a second. Here, thin beds that the normal resistivity tool would not be able to read it. It wouldn't see it. That's the problem. It wouldn't see it at all, especially if you have the thin layer is considered to be the sandstone of the shale, because the hydrocarbon in a conventional reservoir, it would be inside the clean formation, whatever it is, sandstone or carbonate. At the same time, when the thin bed is considered to be the sandstone, which hold the hydrocarbon, and the thick bed would be the shale, which is considered to be having the irreducible water saturation, that would actually mislead the resistivity tool response, and it would give you a very low value of resistivity. However, you have a hydrocarbon in this depth interval here. So vertical resistivity is actually very important rather than the horizontal resistivity, but it comes in a set. So it's a data set that The vertical and the horizontal resistivity comes to you from the triaxial resistivity tool that the service company used to acquire the logs for you. That's it. As I told you here, horizontal is not very important because it's the same as RT. It's the same as the true formation resistivity. True formation resistivity is considered to be the deepest of depth of investigation resistivity log response. So it's equal to the actually, but any good, I wouldn't choose the triaxial resistivity log. I would choose the normal resistivity log. But that's why we go for the triaxial resistivity log. However, I need something from the horizontal resistivity log. We will see it actually in the next slides. It's the important thing about it. The only important thing about it that you can measure the effect or the degree of the anisotropy of the formation that you're going through using the vertical and the horizontal resistivities. Let's see it. Okay, this is the same thing here. Before going through anything, this is the shell content distributions that you can go for, and this is considered to be the laminated lamination beds. This is considered to be shale, and this is sandstone. That was or what may happen to you that would cause the low resistivity pay. Okay, so when I have low resistivity value and then high resistivity value, low resistivity value, high resistivity value in a thin bed or in a thin uh, thickness of uh, a certain layer here, okay, that would be less than the vertical resolution value of the tool itself. So the tool or you tool wouldn't be able to read it. That's the problem. That I'm talking right now about the normal log, of course. Normal log wouldn't be able to read it, but the triaxial resistivity, it has a vertical resistivity component, so it would be read it, and we will see it right now. Okay, this is the same thing. That's why axial resistivity acquisition data in it's a try as you see X, Y, and Z transmitter, and here receivers X, Y, and Z, and using or analyzing the data that I got in those triaxial directions, you can solve it with a tensor as you see here. And the most important values that you have is the diagonal that you have here, XX, which means the conductivity in X direction, Y direction, and the Z direction from the conductivity, then you can obtain the resistivity that you have. Same thing here also. I'm just giving you examples from uh, multiple references. Here, if we need to know how the uh, RV and RH can be calculated, you can go for these formations here. F sand and F shell are considered to be the fractional volume of the sand in a layer, and F shell is considered to be the fractional volume of the shell content in the same depth interval. So, and here our sand is the resistivity of the sand, our shale is considered to be the resistivity of the shale. So let's have all this depth interval here right now considered to be a certain depth of investigation for a resistivity tool here. And this is the shale again, and shale again. So I would get the fractional volume of this whole volume to see what is the fractional volume of the shale. So I would sum up all the fractional volumes of those three layers of shale and do the same thing for the sand here. Okay, and using the triaxial resistivity value, I can measure the resistivity of the sand and the resistivity of the shale. And if now I have the fraction volume of sand and shale and the resistivity of sand and shale, I can use these equations here to calculate the RH and the RV. So you see the reciprocal of the RH equal to fractional volume of the sand over the R sand plus fractional volume of the shale over the resistivity of the shale. RV is considered to be fractional volume of sand times resistivity of sand plus the fractional volume of shale times the resistivity of the shale. That's how you can get the RV and the RH that you have or you need to acquire, but actually you don't need to go through this. I'm just telling you how the tool works. All this, the service company actually are the people who are doing it, rather than using the tool, electric cartridge for pre-processing of the data, or they do it as an environmental correction, and then they give it to the sorry, the producing company to go for their petrophysical analysis. So that's how you can go for the data that you have. I just need you to see something here. Here, the R sand is equal to 20 ohm meter. However, if you would read the R shale here, I don't know if you can see it or not, it's a bit blurry in my perspective here, but it's about 2 ohm meter and 1 ohm meter. This is the horizontal value of the R share, and this is the vertical value of the share resistivity is the same. So that's actually the problem that you have. Due to the so low value of resistivity that you have in the shale content and the relatively high value of the sandstone resistivity with the hydrocarbon within it, of course, uh, that would, if you give an averaging using the normal resistivity tool, that would give you actually about 8 or 9 ohm meters, which is way lower, less than half of the actual resistivity of the hydrocarbon that you have here, of the the resistivity of the sand formation that you have here. Okay, so that would be the problem when you are going through a normal resistivity log. That's why acquiring the resistivity vertically using the triaxial resistivity tool would be way more important than this and way more accurate and precise. Okay, this is let's say a theoretical example. I think with the next one, the next one would be the field examples. So this is considered to be a computed induction resistivity data. Okay, so as you see here, this is a shale formation. This is a shale formation, and this is considered to be a clean formation. The author related to it as the resistivity of sand. So the shale resistivity is considered to be less than the resistivity of sand due to the amount of the irreducible water that the shale have. So having water, it means that I have a lot of salinity. Having a lot of salinity means I have a conductivity. Conductivity is considered to be the reciprocal of the resistivity. So if I have a high conductivity, I would have a low resistivity, and this and vice versa, of course. If I have low conductivity, I will have a high resistivity, and that's what we have here in the sand formation, because sand is considered to be in conventional reservoir with conventional reservoirs. Sand considered to be a very good reservoir rock for a hydrocarbon potential. So going through the same thing here right now, if I'm not taking the sandstone layer here as one bulk of a layer, I would go here and actually get it to be laminated formation, as you see here right now. So this is considered to be sandstone, shale, sandstone, shale, sandstone, shale. Okay, so that's why I have this only slight advance of the resistivity values here. It's because actually it's not a sandstone formation as you see here. No, it's a laminated formation as you see here. But I'm showing you the schematics of what the tool can see. So here, because this is considered to be a normal resistivity tool, it's an induction tool, so it's normal. It would see it as all one block of a layer, whatever it is, sandstone or shale. And it would give you an average of the resistivity value that it can get for the whole bulk as one. However, with more illustration here, I would tell you here right now that this is not a sandstone formation. This is considered to be a laminated or thinly bedded sandstone layers sandwiched between two shale layers, as you see here right now. Okay, This is called lamination. So if I am now at the same depth interval, I dumped these normal resistivity logs data, and I applied a triaxial resistivity model with an outputs of the RH, horizontal resistivity, and the RV, vertical resistivity. So as you see, as I told you, RT is considered to be that we have here, okay, is considered to be the same to the RH, which is the horizontal resistivity, because RH is considered to be the output of the physics principle that the normal resistivity logs use, but it still can be acquired from the triaxial resistivity log. However, when we go for the vertical resistivity value here, okay, you see it's way more advanced, at way more higher than the normal resistivity value that we got here. That's what I'm saying to you. So if I'm only having this hydrocarbon formation here with this only resistivity value, would you perforate it? Maybe you will perforate it if you have nothing to do with the swell right now and you just need to perforate anything. Maybe you have a hydrocarbon in it, so you can just get the money that you spent on the well. But if we are going economically and we are going for a risk assessment process, no, you wouldn't spend thousands of dollars on a perforation job that would actually give you this response of a hydrocarbon resistivity value. Okay. However, at the same time, if you used the triaxial resistivity value, you would see that the resistivity value of the formation, which is the vertical resistivity value, which actually resemble the actual value of the resistivity of this thin bed, it's way more higher than the resistivity value that you got here from the normal resistivity tool. That's why you have a very good application you can make of a triaxial resistivity tool. That's it. So the most important thing that you need to go for is the RV, but you can also use the RH, as the filling between them is considered to be directly proportional to the anisotropic effect or anisotropic effect concentration. So if I have a high separation between the RH and RV, it means that I have a high value of anisotropic effect. If it's and vice versa, you know what I mean. That's it. Okay, this is another uh, example. It's called ZAIT example. ZAIT is triaxial array induction tool. Okay, it's a Schlumberger tool. This is its technical name ZAIT. Its commercial name is RT scanner. Okay, so this log view here right now gives you an indication of the hydrocarbon saturation or the hydrocarbon potential with a gamma ray log, AIT, which is array induction tool of resistivity, and the RT scanner resistivity. So RT scanner resistivity here gives us the values of the triaxial resistivity uh, outputs, which are the RV and RH, horizontal resistivity and vertical resistivity. So I think at upper section here, we can say that we have no problem. Hydrocarbon potential here is not bad. I have a high values of resistivities, actually low from the lowest depth of investigation to the highest depth of investigation, as this is very normal here because this is considered to be an induction tool. So I'm using an induction tool. This means that I am having a resistive poor hole environment, oil-based mud. So oil-based mud is considered to be having a high value of resistivity. That's why the shallow resistivity have a very high value here. So this is normal. It has no problem here. But also the deep resistivity, which is a green dotted line here, having also a high value of resistivity, so it would be still okay. However, I have the shallower depths of investigation tools having high values of the resistivity of the deepest resistivity value, which is 90 inches. 90 inches, we're talking about 225 centimeters, so it's not quite shallow. But having the shallower depth of investigation resistivity tools having a values of resistivity higher than the deepest value or the deepest depth of investigation, that actually would be a problem. Okay. If you work on this well, you need to be sure or be careful when you are going for the saturation modeling that you're going to do regarding the resistivity values. So now let's go, or let's back to our main concept here. So in this lower section of the log, you have the resistivity value is considered to be very low. It's about 1 ohm meter. That's very low. Okay. However, if you use the RT scanner resistivity here, you would say that the RV is the red line here. It's way above the 90 inches induction lock, as you see here. So now the RV resemble the true resistivity value of this anisotropic affected uh, zone that you have here. So this is another example for you. So whenever you have the RV considered to be having a way higher value of the normal resistivity log deep tool, which is the 90 inches, this considered to be actually a very anisotropic effect, a very deep effect, as you see here right now. However, if you didn't perforate, now I'm telling you working on this well, if you didn't perforate this zone right now after you use the RT scanner, now you know that I need to perforate this zone. The normal resistivity log gives me a very low value of it. So that's what I needed to tell you about it. Okay, same thing the horizontal resistivity. As long as you have this ratio equal to 90, you have a very strong anisotropic effect in this depth interval, and you need to perforate it. Okay, so it's not that of a problem if you have the RV and the RH, you would still see it. However, here, if we would see the deep resistivity value, let's take it from here. Okay, so this is the 90, it's all the same, and it all has a very low value of resistivity. It's about 2 ohm meter or something. And in this log, if you go for the red log here, it's way above 2 ohm meter, as you see here. Okay, so I'm here having an anisotropic effect. So I'm having hydrocarbon potential here, and actually it's not that bad. That's it. So after you do this, when you go here for the water saturation from the AIT, okay, you use the resistivity log here, calculated the water saturation from AIT, normal array induction tool. It's considered to be the blue log. So it increases from right to left. So actually, it's very high. Okay. However, when you used the RT scanner tool to calculate water saturation was here represented by the color. It would be lower. That's the water saturation. So having lower water saturation means that I have higher hydrocarbon saturation. That's it. Okay, same thing. It's not different at all. So this is considered to be having low uh, values. Sorry, actually, it's the same thing. I don't need to go for this. This is only having that gives you the core uh, image, as you see. So here you have sandstone, then layer of a shale, then sandstone again, then a thick layer of a shale, thin layer of sandstone, and then a very thick layer of shale, and then sandstone again, and then you goes on. That's it. I wanted to show you about this. This log is going to be the same as the other log, but this one having the cool images, as you see. Okay, another thing that you can use the RT scanner tool to evaluate anisotropy. Okay, this is called Klein plot. Klein plot is considered to be a plot between the RV and RH. RH on the horizontal, on the x-axis, and the RV on the y-axis. And using this tornado chart here, you can know the hydrocarbon potential that you have. This line considers to be representing the volumetric uh, content of shale, and this is considered to be the resistivity of sandstone. Okay, if I'm having the hydrocarbon, sorry, if I'm having the hydrocarbon, yes, in a thin bed, I would find it in this area. Let's go for this one. Okay, this is way more time. This area here is considered to be pay zone as it for you. So if I have a resistivity horizontal and vertical values that would meet up in this area here, this is considered to be a pay zone. Okay, if it's here, that means it's low. Okay, it's not having a very good value, because if you go for the horizontal resistivity, it's in between 10 to the power 0, that means it's 1. So 10 to the power 1, that's its 10. So if I'm having at this area here, it's about 4 or 5 ohm meters. That's not a very good resemblance of a hydrocarbon of a resistivity tool. So that's not good. But if you go up here, the RH goes up, but also the RV goes up. So now here we are talking about 60 or 80 or something like this ohm meters of a resistivity value. So that's way better. So for uh, a field example for it here, here I'm having the shale volumetric content. Here I'm having a neutron and density log. Here I'm having the resistivity values of a normal, sorry, no. This is the RV and the RH and the R sand, resistivity of the sand, the horizontal resistivity and the vertical resistivity from the ZAIT tool. Okay, and here I'm having an anisotropy effect. Anisotropy effect is can be calculated, as I told you. It's a ratio between the RV and the RH. RV over RH is considered to be an anisotropy effect. The more it goes up, the more hydrocarbon that you cannot see. So if you have a ratio between the RV and the RH that's greater than 4 or 5, most of petrophysicists tell you that the anisotropic effect here is considered to be very strong, and you cannot see the hydrocarbon inside this depth interval, so you need to uh, perforate it. Okay, here let's go for the water saturation. It increases from right to left, so the black log is considered to be the water saturation from the horizontal resistivity, or in other words, let's say from the uh, uh, normal resistivity, the depth of investigation resistivity log, and the red log here is considered to be the water saturation from the R sand, or the that you can get. R sand is considered to be the resistivity of the sand formation that you have. Whatever the amount of the hydrocarbon that, sorry, the amount of the fluid that you have inside this sand here. So you see that the water saturation from the sand resistivity is way lower in this depth interval, as an example, is way lower than the water saturation from the horizontal resistivity, which is equal to the water saturation from the true formation resistivity from a normal resistivity log. That's it. And here, if you, I don't know if I can zoom in. Yes, let's do this. Okay. Here, let's go for the RV and the RH. As you see, the points, most of the points are accumulated in this zone here. So this is considered to be a hydrocarbon pay zone. Okay, it's not bad at all. If I am would zoom bad, this cross plot here, it resembles this depth of investigation here, as you see right now. So it's actually having a very good hydrocarbon effect. Okay, so we ended the resistivity value or the resistivity tool to calculate the anisotropy effect. Now let's go for another thing. It's not an anisotropy effect, not resistivity, it's not anything at all. We will use the NMR, nuclear magnetic resonance, to obtain the hydrocarbon potential that I cannot see. So let's come here. This is considered to be a resistivity values at a certain depth interval, as you see here. But the deep lateral log, as you see, it's the shaded line that I'm going through right now. It's not that high. It's between 1 and 10 ohm meters. That gives you a hydrocarbon saturation resemblance of a very low hydrocarbon saturation. So if you would say this, you wouldn't uh, perforate this uh, zone. It would give you, let's say, 10% of the hold up in the production tube considered to be occupied by a hydrocarbon, which would be very low. So that wouldn't be very economic. You wouldn't do this. But at the same time, let's look on the T2 distribution, the porosity T2 distribution from the NMR tool. So here, this blue line is considered to be the bound fluid, the bound fluid volume cut off. So every fluid that I have occupying the pores of this green humps here left to the line is considered to be bound fluid. I will not be producing. I cannot be producing, at least now. We don't have a let's say a technology that we can actually produce the bound fluid. Maybe we can go for AUR or water flooding or something like this, but after all, it's not very popular till now, at least in my area. I don't know about you guys. Could you please, I don't know, maybe someone is talking in the chat box. Give me a second. Okay, okay, no one. Okay. Uh, so again, as I told you, so this is considered to be the bound fluid uh, cut off. But this red line is this thing that we need to go for here right now. So this red vertical cut off line, it's a line that, let's say, separates the hydrocarbon from what is not hydrocarbon. Because if you would see here, this is a line that was written from a value of the T2 relaxation time of hydrogen equal to 210 milliseconds. As you see here, it's a oil water phase line. So whatever I have on the right of this line here right now is considered to be a hydrocarbon. So you see, I have a very good amount of porosity that actually relaxed or had to have a very long time to be relaxed. And by very long time, I'm meaning 1 second or something like this. Just not to get me wrong if you don't know about NMR. Long time regarding NMR, at most, it's about 5 seconds. That's a very long time for the relaxation of the fluid that you have inside the pores. So as you see here, using the NMR data, we can know what is the amount of the hydrocarbon that we have without using the resistivity values. So this was a situation of a low resistivity pay example that I wanted to show to you. As you see, the value of the resistivity is not that high. It's from 0.1 to 1000. Sorry, this is not a normal log. This is a logarithmic log. So here we are talking about uh, 5 or 6 ohm meters at most. And here, at the same time, we are seeing a hydrocarbon potential occupying a very good amount of porosity, as you see here, right to the red cutoff line. That's it. So NMR is also very useful for this. Also, NMR can be having some kind of extra services. We call it Sometimes you can measure the saturation. With the saturation from NMR, you can have a diffusion T2 map surface. Also, you can go for the CMR plus or the magnosphere for some kind of T1, T2 map, but this is not considered to be a normal NMR output. So the client should pay more for these services. It's actually services that can give you a direct with a very high accuracy and precision, a direct measurement of how much hydrocarbon that you have or how much water that you have without going through the resistivity log. Okay, last, I think, or the last tool that we need to talk about is considered to be the dielectric scanner. I think we ran of time. I don't know if I can continue or not. I just need about more 5 minutes or something. What do you think, the
Okay, take your
coordinator,
time.
please?
Take your
Okay, okay, okay. Thank you. I just need about 5 or 10 minutes more than that. That's it. The dielectric scanner tool, just to save time. If you want to know about this tool, if you want to know about the RT scanner, NMR, all this, I will recommend certain brochures and guidelines for you to read at the end of the webinar. So just now, let's go for the application of the dielectric scanner tool. Dielectric scanner tool is considered to be a tool that its physics principle mainly related to something called permittivity. Permittivity, it means how much does the formation permit the current coming from the tool to the formation. That's it. That's it. That's very easy. It depends on the current permittivity, how the or how much the formation would permit the current to transduce or to be transduced through the formation. And that's it. By this, by this, could you please stop doing this? The I don't know what are you. Maybe he's someone is trying to say something, but I cannot open the chat box. Sorry, just write everything in the chat box, and I will answer you in the at the end. So let's see here the resistivity logs. We have a very high values of resistivity logs here. So there is no problem with the saturations. The green here, the green volume here, considered with the saturation or the residual of the oil saturation or the moved saturation oil. If you would know about why this considered to be the residual saturation of oil that I have this much, because the only problem with the dielectric scanner tool that it has a very short depth of investigation. The deepest depth of investigation that the dielectric scanner tool can go for you is 4 inches. 4 inches, I'm talking 10 centimeters. That's still in the flushed zone. So the hydrocarbon that you can calculate, the hydrocarbon potential that you can calculate in this depth of investigation is considered to be residual oil saturation or the moved oil saturation if you would subtract it from the total water saturation. And that's it. But how do I know that the amount of the dielectric saturation measures is considered to be hydrocarbon, not a water? Okay, I'll talk about this. Let's just go for the resistivity values here before first, and then I'll go for the water and oil classification. So you see here, I'm having a very high value of resistivity, as you see here. So having a high amount of hydrocarbon, that's okay. There's no problem. Okay, but let's go down a little bit. Okay, let's go here in this depth interval. You see the resistivity value here of the deep resistivity value. Let's take the red data here of the resistivity value. I think here it begins from uh, 0.2 to 200, and here it's about 20, then it's about 200 here. So here it reached about 200 ohm meter. Okay, however here it goes or it went up straight to 2000. Okay, so here having a low value, or not low, 200 is not low, of course, but lower value of the resistivity value, if we compare it to the upper section here, the hydrocarbon saturation would be less. It should be less. But if you would see the green and the orange is considered to be the movable hydrocarbon, the green and the orange uh, volume here is considered to be still very high. However, the resistivity went down by more than 1,000 ohm meters. So we are here having a low resistivity pay. So now I think by this example, you should now know that having low resistivity pay doesn't always mean that this resistivity should be 0.5 ohm meter, or from 1 to 10, or from 1 to 5 ohm meters. No, it can be exceeding 100 ohm meter and it's still the resistivity pay. Okay? This depends on the amount of the anisotropy effect that you have. It should sometimes, it's considered to be a low anisotropic effect, so it wouldn't affect the resistivity value so much. But sometimes it's considered to be a strong anisotropic effect, so it would lower the resistivity to the most that you have, which is about 0.5 or 0.6 ohm meters. And I saw that before, actually, in my country. A certain producing company produced more than I think 10,000 barrels. I think it was 10,000 barrels. Sorry, that was 3 years ago or something. I don't remember so much, but it produced an amount of 10,000 barrels of hydrocarbon from a depth interval that showed a normal value of resistivity corresponding to this depth interval equal to 0.5 ohm meter. Okay, so resistivity log or normal resistivity log is not always right. So you just need to know this, and you need to study if you want to be, let's say, a good petrophysicist. Well, logging only would not be a very useful thing for you. You still need to go for the geological strata effects and something like this. So let's go again for the resistivity values. So I told you that the resistivity here is lower than here. So the hydrocarbon saturation here should be considered to be lower than here. However, we don't see this here. The water saturation or the oil saturation considered to be about to be the same. So why is this happening? I need you to see something. See this blue line. Okay, you know what? No, let's not. Let's take it as a total. See this red line that I have. It tells you, or it says, dielectric scanner, deep water-filled porosity. Okay, so somehow I cannot go through this right now. It would take so much time. But somehow dielectric scanner, by the physics principle of the current permittivity, as I told you about, it measures the amount of the porosity that you have that has 100% water occupying that porosity. It's called water-filled porosity. So if I have now this water-filled porosity fraction, and I subtracted it from the total porosity that I have, what would I have? I will have the amount of the porosity volume that has no water inside it. So if I'm not having water inside this filled water porosity, what should I have? Yes, exactly. I have hydrocarbon. That's why what you have here. So the water filled porosity here is considered to be very low, as you see here. Okay, as the same here, it's considered to be also very low. This is the water filled porosity here. So, and this red line, sorry, this black line is considered to be the total porosity that you have here. Okay, so the difference between them is this green area that you have here right now. So this is considered to be the way that you can use the dielectric scanner tool to have a good interpretation for a low resistivity pay. Okay, same thing here. There's no problem, or there's no difference between the last example and this one. The only thing that here, the well log data of the water saturation from dielectric data and the dielectric water porosity is now verified by core data. These black dots that you see in front of you, and I think that you can see it matches pretty well. It's not bad at all. So that means that the precision and the accuracy of the tool itself, it's very good. It's not it's reliable. Okay, I think this is the last example that we have, an FMI example. Okay, you can see here that I'm having a very low value of resistivity too. We are talking 2 ohm meter or 3 ohm meters along the whole different interval that we have here. Okay, however, this is considered to be the static or dynamic image of an FMI tool. FMI tool is considered to be the full bore micro imager. It's a tool that can give you an image of the microstructure of the pore hole that you have. So, as I told you before, in laminated formation, shale is considered to be having low resistivity, so it's conductive, and vice versa for the sandstone when it's occupying hydrocarbon. So, going through this heat part here, conductive is black and resistive is from yellow to white. So whenever I have black here, I'm having shale. Whenever I'm having yellow here or white, I'm having sandstone. So I think that you can see that we have a very obvious lamination or a very obvious anisotropic effect that we can see here right now as in front of you. However, I'm having a very low value of resistivity, but by showing you the data that I can get from the FMI data or the OPMI imager, sorry, OPMI is oil based mud imager. It's the same thing as FMI, nothing different. But FMI or the borehole imaging, it has two principles for reading the data. Either it's sonic, so you can use UEPMI, or you can go for the image from conductivity or resistivity. That's why you can sometimes use the FMI when you are going through water-based mud, and OPMI when you are going through water-based mud. Sorry, oil-based mud. So you can see here that we are having lamination or an isotropic effect. However, I have a very low value of resistivity. So this gives you an indication that you may have a hydrocarbon potential in this different interval. So you can do one either of two things. You can run dielectric tool, or you can run NMR tool, or you can run RT scanner tool, or you can just take some course in this different interval so you can see the hydrocarbon potential that you have from the special core analysis data. Same thing here, but I think here it has everything that you need to go for. Here you can have the horizontal resistivity in the blue line, as you see, and the vertical resistivity is considered to be the red, as you see in front of you here. So I have a very good amount of hydrocarbon here regarding the resistivity. When we went for the ELAN models, it gave a very good hydrocarbon effect, as you see here right now. This ELAM model is from the normal resistivity tool, and this ELAM model is from the RT scanner saturation mod. As you see, the RT scanner showed you a very good amount of hydrocarbon along this anisotropic zone here. Also, when you go for the FMI image, you can see the lamination, the black lines here, or the black faults here alongside bedded, actually right upside of it or downward of it, a very white or whitey, it goes to whitey color. So now you can know that I'm having a sandstone over shale, then sandstone again, then shale again. So this is considered to be a laminated formation. So the value of the hydrocarbon here acquired here by the RT scanner is considered to be very well interpreted if we also had a look on FMI. So both of them tools go along in the interpretation. That's it. Thank you very much. Those were my references that I had um, to go through this presentation. This is a paper, Triaxial induction, a new angle on the old measurement. This paper is very good for RT scanner if you need to know about it. You will find it on Schlumberger website. Also, the lowdown on the low resistivity bay, also on Schlumberger website, and the dielectric scanner application considers to be like a manual. You can get the brochure of the tool itself also from the Schlumberger website. My recommendation to you, there is a new release that Schlumberger had done about 2 months ago or something like this, a tool that have been used for more than 11 years or 12 years right now. It's called Ecoscope. Schlumberger had just released the guideline, they use a guideline for the tool on their website as a PDF file right now. So I very encourage you. I so much encourage you if you are uh, into petrophysics, you should read this book. It's very good. It's very to the point. There's no much of literature inside the book. You really should read this book. Thank you very much for listening. That was Abdel Fattah Rashid for you. And that's it. Thank you very much for listening.
Thank you, Engineer Abdel Fattah, for such interesting webinar. We have some questions.
Okay.
Uh, one second. So the first question, for determining the anisotropy, what should be the cutoff value for low resistivity bay as compared to higher values?
Well, the cutoff, I think that I can relate to this question. Yeah, the problem here that the cutoff or the pay cutoff is not applicable no more. The problem here that you cannot just perforate a depth interval that's equal to, let's say, 10 centimeters or something like this, and then leave about 2 centimeters below it or above it, that without considered to be without perforation, which is considered to be the thin bed of shale. So you just, what you do here, that you perforate all of it. That's it. That's the problem. And after that, you can plug the water saturation or the water flowing perforations. But to be fully honest with you, I saw a case of this before in my country. They perforated all the depth interval. They didn't, let's perforate those 10 centimeters and then let's leave the lower 5 centimeters and let's perforate the lower 20 or something like this. No, they perforate all of it, and then using a PLT they can plug cement, using cement plugs to plug the water flowing from the data, from the pay, sorry. That's it.
Okay, thank you. Formation contain components such as hematite or iron component. It will affect on resistivity.
Yes, of course, with affect resistivity, hematite and ferrous, and also the copper. Those are all considered to be conductive minerals. So if I'm trying to calculate or to measure the response of the resistivity at a certain depth interval that have such minerals, it would of course lower the resistivity value less than what it should be. So that's considered to be a way for another case of a low resistivity bay.
Okay. The other question, please define RH and RV.
Please design. Okay, I wanted to go for this, but the problem if I went for the physics principle of it, it would be so hard. It wouldn't have time for it, to be fully honest.
Okay.
Uh, but just give me a second. Maybe I can do it. Just give me a second.
Yeah.
I'm just looking for a graph. Maybe I can do on this. Okay, here. Okay, this is considered to be a laminated formation. Okay, I have a fraction of sand, then shale, then sand, then shale. Okay, the problem here that normal resistivity log wouldn't be applicable here. So you need to go for the RV and RH from the RT scanner too. RH, which is the horizontal resistivity. If I'm having, sorry for the LEWD log here or the deviated well, just imagine that I am having well at this area that I'm having here right now. It's a vertical well, okay? Horizontal resistivity, okay, would be like this. The direction of measurement would be horizontal, okay? So if the wireline tool in this well here right now measured the value of the resistivity in a shale here and the value of the sand here, okay, one of with a normal resistivity tool, not the RT scanner. I'm now talking about the normal resistivity tool. Normal resistivity tool here right now, it wouldn't catch one of them. It's impossible for the tool to catch the resistivity value for the shale here and the sand here due to something called a vertical resolution of the tool. I cannot illustrate this to you right now, but if you have a Vimeo account, Vimeo, you would know Mr. Dave Kennedy presentation about vertical resolution and low resistivity pay. It would be very good if you would see this. It's on vimeo.com, Dave Kennedy, low resistivity pay. Okay, so it wouldn't reach the value for those two bits at the same time. That's here now why you use the RH and RV from the RT scanner. The RH is considered to be the same as the normal resistivity, deep resistivity value. It measures horizontally and it cannot catch the values of the resistivity from both of them. No, it would only give you an average of both of them pads here, because the vertical resolution of the tool is not that high. Okay. However, the RV vertical resolution, the vertical resistivity, it's not from its name, it's not measuring horizontally. Somehow, the vertical tool from the well inside here, now it can measure the vertical resistivity here. So it can go through the physics principle of the tool regarding the vertical resistivity, can go through the whole vertical thickness of whatever the layer that you're going through here right now, and it can give you way more higher value of the resistivity rather than the horizontal resistivity value. I hope that I would make you understand it even a little bit more.
Okay, thank you. In case that we have thin sand, almost
Okay,
2 feet.
almost 2 feet. Okay,
Yeah, can't we calculate the water saturation from the RH?
sir, that's the problem. Well, whoever asking this question, that's the problem. Whenever you have more thin layer of sandstone, that's even make it harder to calculate the water saturation from it. That's harder. It's not 2 feet that you can now calculate the. It's now better or something like this. No, whenever you have the thickness of the layer that you are investigating, whatever the layer is, sandstone, carbonate, or clay or shale or something like this, the more it's thin, the harder that you can have a well-log response from it. But it can be done if you are talking about the 2 feet thin sandstone layer. It can be done. You can get a very good value of the resistivity from it, but not from the horizontal value. It is still from the RV, from the vertical resolution data. That's it.
Okay, thank you, Engineer Abdel Fattah, for such interesting webinar. And please, anyone that has any question, please drop it into the LinkedIn event chat. Okay, thank you all for your attendance. And if anyone doesn't fill in the form for certification, please fill into the form, because we won't send any certificate for that doesn't fill into the form into the Zoom chat. Thank you all, and thank you again, Engineer Abdel Fattah, for your time and for your effort.
Thank you very much. Have a nice
Thank you.
day.
Have a nice day.